Hey guys, today I'm going to be teaching you a little bit about logistic growth. So one of the main things you're going to want to know about logistic growth is how it differs from just normal population growth. With population growth, it is going to be solely exponential and it's going to neglect a death rate. So as time goes on, the population is just going to keep increasing. Now with logistic growth, it is going to incorporate some kind of carrying capacity and it'll be more accurate to normal growth, like the growth of a population of a city or how bacteria grows. Here are the equations of the population growth and logistic growth. We are going to be dealing mainly with the logistic growth today. Now you may be wondering, what do these equations mean? So when we look at the differential equation of population for logistic growth, it will be dp dt, and it will be equal to little r times p times 1 minus p over k. And you may also see this as dp dt is equal to big R times P times K minus P, where your little r is going to be equivalent to your big R times K. Now, your K is going to stand for your carrying capacity. So if your city can hold up to 200 people, your carrying capacity K will be equal to 200. And your little r is going to be your constant of proportionality or your growth factor, and that's going to be something you solve for each situation. Now, for the purposes of integration later on, we are going to be dealing mainly with equation number 1. So if you come across something in the form of equation number 2, this is how you convert it. So if you're given your dp dt is equal to 2p times 3 minus p, you're going to recognize first that your big R is equal to 2 and your k value is equal to 3, as you can see from this equation here. Now, to convert that to equation number 1, you're going to know that you're going to have some value here times p, and you want this to go to 1, so you're going to divide everything by 3. So you have 1 minus p over 3. And now because you took out a 3 from the parentheses, you're going to bring it out here. So you take your 2p times 3 and you'll get 6. So your new r value, little r, will be equal to 6, and your k remains as 3. Now we're going to go over how to antiderive dp dt to get your p of t. So first you're going to start with your equation, dp dt equals rp times 1 minus p over k. And you're going to move everything that has p, so your p times 1 minus p over k, over to this side and your dt over to that side. Now you are going to take the integral of both sides. Now for the purposes of making this easy to work with, we're going to multiply it by k over k. Now we're going to take this side right here off on the little sine over cosine. Get it? Take it off on like a little tangent, because sorry, that was a bad joke. But we're going to deal with just this right here. And we're going to do partial fraction decomposition to make it easier to integrate. And then you arrive at this as your answer. Now we also need to find what a is equal to. So we are going to go back to this step right here. We're going to take it in terms of t equals 0. So when t equals 0, k minus p sub 0 over p sub 0, where our p sub 0 is equal to our original population. Next, we're going to go over 4 limits that you need to know. So here we have our basic logistic growth function, and we're going to be looking at the limit as t approaches infinity and negative infinity of both p of t and p prime of t. So first, this one, as t approaches infinity of p of t. So here's our p of t, and we can see that as time goes on to infinity, our p of t value is going to be approaching k. And also note that since this is a horizontal asymptote, it can cross and go above like this, but it will eventually go back to k. So for this we can put that as equal to k. Now the limit as t approaches negative infinity of p of t, as time goes on to negative infinity, we can see that this will eventually be going to 0. The limit as t approaches infinity of p prime of t, so that's going to be the rate at which it is increasing. So as it goes on to infinity, we can see that the graph flattens out. Therefore, our p prime of t will be equal to 0. And the same thing here. As it approaches negative infinity, our rate will be going to 0. So the only one you need to keep in mind is the limit as t approaches infinity of p of t, because that's going to be your k value. Everything else is 0. So it's a fairly easy thing to remember. Also note that the point of inflection of a logistic growth function is going to be at k over 2. So if your k value is 200, your point of inflection will be at wherever p of t is equal to 100. And this will be where, if you're thinking conceptually about it, your dp dt is going to be growing at its fastest, and it will begin to decline. Okay, now for an example problem. So say we have a certain city that can sustain about 1,500 people. And as of year 2000, where times equal to 0, the population is 255, and in 2001, the population is 298. Now for part A, it's asking us to write an equation for the logistic differential equation. So that's going to be our dp dt. And what you're going to want to do before you even start a problem, you're going to want to list out your givens. Now, our dp dt, we're going to want to follow the formula that we have. So we have rp times 1 minus p over k, and we'll just substitute in what we know, which is rk. So rp is equal to 1 minus p over 1,500. And that's all that we can solve for. Part B, it wants to know the 4 limits of the function. So we just did that, and we know that everything is equal to 0 except for the limit as t approaches infinity of p of t. So we have limit as t approaches infinity of p of t, and that's equal to our k value, which we already know, so we know that's 1,500. And then everything else is equal to 0. Now part C is asking us to solve for p of t. So we're going to refer back to the formula we solved for earlier. Now we know our k value, and we can solve for our a value. So, and that is about 4.882. So let's plug everything in. Now from here we can solve for r by using p of 1. So we know our p of 1 is equal to 298, and then we will plug in 1 for our t. And now we just solve for r. Now that we have our r, we can plug everything back in to get our original p of t. Sorry, this should be 0.19, not 1.9. Now part D is really simple. It's just asking for when the population rate begins to decline. And as we stated earlier, that's going to occur at the point of inflection, which is going to be when p of t is equal to k over 2. So we want our p of t to be equal to 1,500 over 2, which is 750. And then you're just going to make this equal to the equation that we solved earlier. And then you're going to solve for t. And you're just going to plug that into your calculator, and you're going to get out that time is equal to 8.30229, about. And that is your answer. Now common places to make error would be where, let's say like, I made my error here, I accidentally put my decimal place in the wrong spot, and that could lead to a lot of problems because your exponent is now a completely different number. One last thing to watch out for is, let's just say you're more comfortable with the second equation for differential logistics, where you have dp dt is equal to big RP times k minus p. If you're working with this equation for your, let's say like part A, you're going to have to be careful with when you solve for p of t. Make sure you convert this to the other equation if you're using the formula I gave you. And make sure you're aware that this r is different from little r.